So, good morning. That's Wednesday. We already have the discussion for the switching fabrics, specifically for the prefix matching, longest prefix matching. And today we will continue to have the details for the switching fabrics. All right, so here we have the switching fabrics. And you can see we have these. So we have switching fabrics here. And we expect to have high speed. So how to have a high speed? Later we have some different approaches to achieve high speed switching fabrics. Well, so why we want to have switching fabrics? Because we want to have the packet transfer from input to the output. And so that we have the switching, the goal of switching. Well, we want to have a high-speed switching fabric. Therefore, how to have a high speed? In fact, we expect to have this. Possibly, we will have the multiple of the input or output line rate. All right, for example, we have the rate R here. And we expect to have the multiple of the lines. Well, for example, we have n input lines, or maybe we have n output lines. Therefore, the expectation, we expect to have n multiply r. This is ideal rate. It doesn't mean we can achieve it as we expect. No. In fact, we want to have the highest rate, n multiplies r. Well, so this is the ideal rate. So how to achieve the ideal rate nr? Later we will already know how we achieve it through the three different approaches. So we know we want to have the packet transfer, and the switching rate, if possible, we want to have, for example, n equal to the input line or output line. Then we expect to have nr. So we have n multiplies the line rate. Well, how to implement? We have three types of, actually major three types of switching fabrics. First one, we apply memory. And second one, we apply bus. And the third one, we want to have the interconnection network. Well, first of all, we have the switching via the memory. This is the first generation. So you see, it's a first generation. Well, so we apply memory. Of course, the memory will be controlled by CPU. And CPU can have the packet transfer control. Therefore, CPU will copy packet to the memory. And then from the memory to the output. From the input, copy to the memory, then copy it to the output. That says we have the speed limitation by the memory bandwidth. You can see we have two bus crossing. So that's why we have the speed limitation by the memory bandwidth. That says how fast we can copy and how fast we can return the packet to the output. Well, this is the first one, first generation one. Why do you think it's the first generation? Because we have the computer, and we ask the computer to provide the function of switching. it's really easy if we have a computer first. Well, so that's why this is the first generation switching fabrics. So first of all, we copy, and then we can put the packet to the output. All right, so this is the switching via memory. And next one through bus. So we have a datagram. Previously we call packet, or here we call datagram, from the input port to the output port. And currently we have the shared memory. If we have the shared memory, then we have the bus contention. All right, so of course the limitation is the bus bandwidth. If you want to have an example, the current example is this one, Cisco 56000. So we have this example. Today we have the possible switching fabrics via bus. And the speed for this one is 32. And if 32, then maybe for some generation, actually this one is sufficient. And currently, if you think we expect to have an even higher one, then you don't think so. But at least, for some generation, 32 gigabits per second, it's sufficient speed for the access. At least it's the access routers. So here we have a bus, and with the bus then we can have the packet transfer. Well, next one, we want to have somewhat like we have the interconnection network. And so that we have the crossbar networks here. And we have the interconnection for this one. And so that we expect, okay, if we have the setting, then it will be easier to have the proper packet transferring. Well, of course, this is the initial one. We can have the interconnection network. And here you can see interconnection network for part of 1, interconnection network. Therefore, we can have interconnection together. Therefore, we have a multi-stage switch. All right. So you can see, for example, we can have the fundamental N by N, and then we can have the other switching fabrics, and so that we can have the multiple or maybe even larger inter-switching networks. So we can have the fundamental switching fabrics, and then we can have the others. So up to now, we expect to have the interconnection initially. Once we have the interconnection network, then we can expand. So we can have the expand interconnection network. Therefore, smaller one to the multi-stage one, and therefore we expect to have larger. Somewhat like larger N input lines. So we expect to have an effect like this. That's why we have the multi-stage switch. Well, why we want to have the multi-stage one? Or maybe later, yes, later we will have the parallelism. And currently, multi-stage, we can have the concept of parallelism, 平行. So, why we want to do that? Actually, we can have the whole datagram. But we can make it into the smaller one So we have the fragments. So fragment or fragmented datagram into the small length cells. Here, cells actually equivalent to the datagram, but we have a smaller size datagram. We can call it is a cell. So we can fragment datagrams into smaller cells. As on the smaller cell, we expect to have the faster switching. So we switch cell through the fabric and then we want to reassemble. And currently, we want to based on the parallelism or based on the multi-stage switching. Why we want to make it faster? Because if we process a really large datagram, it is not easy for the switching fabrics. So we can break the fragment into smaller cells. Based on the smaller cell, then we can allow the cell going through the switch, the interconnection network. Of course, we still want to have the original one, so we can have the fragmented one. Then we reassemble after the interconnection of switching fabrics. So we can base on this and so that we can achieve it. However, we have the complexity. We need to have the fragmentation. All right. At least we assume we can achieve it, so we have the fragmentation first, then we can reassemble. Well, because we expect to, so look at this. You see? Again, we have the fragment, and then we have cells. So this is a concept. If we have the smaller cells, then we can have the switching easier if we have the smaller cells. Well, that is the multi-stage interconnection network. And in fact, with that node, we can have the parallelism. If we have the parallelism, then we expect to have the operation in parallel. And the operation in parallel, previously we can have the multi-stage one. For example, here, this is a multi-stage one. And we can think it's a plane. And based on the plane, is it possible to have the multi-stage again? We have a plane 0. And we have a plane 7 or an even larger one. And so that we can have the input again, so we can make it larger based on this, because we want to have the parallelism. Therefore, we can expand and make the interconnection network larger. If it is larger, then we allow more input rate because of more input numbers. And because of more input numbers, and then the speed will be higher if we expand and multiply the rate. Well, if we have the interconnection network with this kind of concept, then this approach can be expanded easier. So that's why we want to use this, and this is the newest one for the switches. Well, so we can speed up and we can scale up parallelism. It's easy to speed up, to scale up. Therefore, this one is a popular one. Then we already have a possible example. And we have the example here. We have 8 switching planes. And within the plane, we have the interconnection network. And that interconnection network contains 3 stages. So that's why we already have a multi-stage first, and then we want to have the the parallelism to exploit the possible rates or exploit higher rate. If we have that one, then it's possible to have 100t because t beats per second. So t higher, and t actually equal to 10 raised power to 9. So, sorry, g is 9 and then it's 12. So we have an even higher rate, which is a capacity. Therefore, this is a good approach to have the switching. Well, so up to now, we already have 3 approaches to have the switching fabrics. The first one, memory. Second one is bus. And the third one, actually, it's the interconnection network. All right. And finally, interconnection network will be easier to have for the expansion. We can speed up, we can scale up. So we expect that one. About the 3 possible types of switching fabric. Think about this and talk to your neighbors about the 3 for 1 minute. So think about this. I think for the 3 types each, it will, they will be okay for you, right? And we focus on, actually, it's the core of the switches. And we have the input, and also we have the output. Is it possible to have a queuing? Of course, it says yes. Why is yes? Think about this. Even we expect the switching fabrics can process faster. But sometimes it's possible to have the input rate lower than the capacity of the higher rate. Input rate higher than the capacity of the switching fabrics. So you see, a switch fabric is lower than the input ports. Therefore, we have a queuing. And likewise for the output port. So we have a queuing as well. And at this, we talk about the queuing at the input port. Because of a queuing, then we will have a queuing delay. And we have a loss possibly because of buffer overflow. Buffer overflow at the input port. All right, so we have the input port queuing. And furthermore, we have the head-of-line blocking. Head-of-line, that says we have the queue datagram at front of the queue, will prevent the other in queue from moving to the next one, actually to the output port. So head of line here, head of line, and head of line. And we have multiple colors from different input ports. If so, then some of the processing will block the other head of line. So that's why we call head of line blocking. Well, follow the current possible scenario. Output pole contention. Here we don't have only one rate. Here we have a rate. Rate data frame can be transferred. And we assume the lower rate with the low priority. Well, so this is the possible head of line blocking. And next one, we assume one packet time later. And we have a green one. And green one wants to access likewise green one with the head of line blocking as well. So here it says, because of the capacity lower than maybe some processing, so we have the queuing. However, we need to move the packet to the next stage. At the next stage, if we have one processing, then we will block. We will ask the head of line stay there or maybe block it directly because we have we expect to process further. Or maybe at least we have a queue. We need to ask the diagram there to hold it, and later if the possible output is ready, then we can move it to the next one. So we have the blocking. Blocking doesn't mean we drop it directly. At least we have a blocking. And likewise, for the scenario at the output pole, if we have a faster switching fabric, so we have many packets to transfer to the output pole. And if the link with the rate lower than the switching fabric, then we should have the queuing at the output pole. So it's okay to have the output pole buffering. And for the buffering, actually, we can process for sure. However, if we have the limit size, then we have the drop policy. Even previously, we don't expect to have the drop policy. And in fact, you can have a drop policy at the input pole. And currently, we can have the drop policy at the output pole. Why we discuss the drop policy at the output pole? Because even we have the drop there, we think, okay, those packets cannot reach the output. And once we have the final stage to go to the line, and then we need to have the determination to keep it or to drop it. So that's why we have the drop policy specifically at the output pole. Well, it says, yes, if we have the buffering, actually we will have the packet loss possibly, or diagram loss possibly. Why? Because we don't have a large enough size for the buffer. And actually, we have the congestion mentioned in chapter 3. Well, even we have the losses, but maybe we try to have the efficient scheduling. And efficient scheduling will try to have the possible management. And hopefully, we can avoid the packet losses. Well, scheduling, if we have a scheduling, then it doesn't mean we allow the packet to be processed in first in and first out manner. So, FIFO again, first in, first out, no. And therefore, we will have the priority based scheduling. Why? Priority based scheduling. Of course, for some string, actually they expect to have the higher service, and so that we should have a higher priority associated with that string. So we have a priority, and then we need to determine which datagram or which packet should be served a bit maybe using a higher priority. Therefore, we already have this one. Well, we already have an alert. About scheduling, it's really important, but later we go through scheduling and then you know how we have the different scheduling. And scheduling is an issue, so that's why we already know, okay, it's really important because of the output pole queuing and buffering. So we need to have the proper scheduling. And because of this, so it's really important to have the further development of scheduling. Oh, sorry, maybe I forgot to switch back. So output pole queuing so that we have scheduling. So of course, because of output pole queuing, then we have buffering. And actually, we have losses for sure. And even we mentioned it's really important to have scheduling. But not right now. Later, we will already have a discussion for scheduling. However, we still continue to check if we need to have a buffer. Then, what's the size for the buffer? In fact, we have a rule of thumb. A rule of thumb today have this one. Because of a rule of thumb, so you can look up possible draft or something else. So that you want to know why we want to have a formula like this. We have this one to then have the possible size. If we have the size, then it says, well, long RTT. We have the exchange. Longer RTT, of course, we should have a larger size. So it makes sense. And also we have C, capacity higher. So we should have a larger one as well. And for the input line, because of an input line, then we can process faster. So that we can reduce. But what's the size to reduce? We use square root of n, and so that we can reduce the size. Well, maybe we have some way to explain this one possible makes sense. And of course, you can use it directly. So rule of thumb, what it means, this one. In fact, in the past, maybe some researcher think, okay, we can follow some of the rules. And for most of the researchers think, okay, yes, it's useful. So finally, we have that rule of thumb to have the setting for the size of the buffer. So this one. All right, if we want to have the buffering, specifically, we talk about the buffering for the output pole. So this one actually allows the buffer size at the output pole. So this one, just for your reference. All right, so maybe, yes, it's our time to have the antenna checking. And same for you to have 2 minutes. I think for students in the classroom, finish, right? If no, raise your hands. But because we have students online, so let us still wait till timeout. So we still have around 40 seconds. And possibly, maybe some of you are online. For example, Quentin, right? Well, so we have a buffer, and of course, we have the buffer management. And buffer management, we talk about scheduling later. And previously, we didn't know it's really important to have the design for scheduling. In fact, that's one. Therefore, we want to have scheduling, and then we use the term buffer management. And we have the buffer here. We have the abstraction. That says we have a concept of a queue first. So we have a queue. And we have the server. Actually, this is a service rate. Service rate. All right, so we have the server with the service rate, and it's the link rate. And within it's the server. So we have the concept, we have a server here. Well, so of course, for buffer management, previously we didn't know the drop policy. So we should have the suitable policy to drop. And of course, we have the priority. Priority to drop it or not, and priority to process further or not. And of course, we can have some possible marking to have the congestion, or to have some other possible operation as well. So we should have many action, and so many action, we have the buffer management. Specifically, we want to discuss scheduling. All right, so specifically, we want to discuss scheduling. Scheduling, first of all, we have the previous one, FIFO. Oh, here it's first come, first serve. I think you know first come, first serve. For example, you line up before a restaurant, and then the servants will serve you using the menu, unless we have the other principle. And also, we may have the priority. All right, so for example, airplane, we have the priority seats. And for the others, for fairness. For fairness, then we have round robin and what if fail queuing. Therefore, let us check what that means. So FIFO, or first come, first serve, I think you know it's really easy. And I didn't have the real example. For example, you want to line up so you want to line up for your lunch boxes, then it's a really common real world example. And actually, we can have a priority. That says we need to have the priority setting, and possibly you can have the number. For example, normally we have a lower number to stand for the higher priority. You can have a packet with the priority 0, the highest one. Then, for example, you can have a priority, for example, 10. 10 may be really low priority. But you can have 0 and 1. 0 it's high, and 1 it's low. So possibly you can have the association. Once you have the association, we will serve, for example, all right, this is the priority associated with 0, and this is a priority associated with 1. Something like that. But if you don't like the numbering, you can have a high priority, low priority. However, it doesn't mean we have low and high. We have lowest one and we have a highest one. So in fact, we can have multiple label. Because of multiple label, therefore we want to have the numbering. Based on the numbering, we can implement that priority setting. Therefore, if we have the possible marking to have the highest one, of course, we serve the highest priority queue unless the buffer is empty. So we can serve the next priority and so on. So we have the priority. For example, we have these. And currently, maybe you follow 1, 2, 3, and 4. And here, of course, 1 is 1, 3, 2, 4. And maybe you don't think we have the priority. But look at this. We have 1, 3, 2. But currently, we don't follow the numbering. Actually, we follow some specific reason. Okay, 1 is the highest priority. 3 actually higher than 2. So currently, we don't follow the numbering. Actually, if we have the numbering, we can enforce. But sometimes we have the number for, okay, the first packet, second packet, third packet, fourth, the fifth packet. So here, the numbering for the packet arrival rather than the priority. And in fact, we try to emphasize even we have packet 3. But packet 3 has a higher priority than packet 2. But packet 1 higher. Currently, we don't have any information 1 higher than 3 or not. Perhaps 1 comes earlier, so we can serve it at least higher than 2. So we can serve it earlier than 2. As for earlier than 3, up to now, we don't have the information to tell. Or maybe you think, okay, yes, so higher than 3. If so, that's okay. But at least 1 comes earlier than 3, so 1 can be served before 3. And for 1 and 2, actually, 1 comes earlier, so 1 can be served as well. And 2 and 3, because waiting for the service of packet 1. So, of course, 2 and 3. 2 and 3 with the possible setting of a priority, because we allow packet 3 has a higher priority than packet 2. So here we allow packet 3 to be served first before packet 2. Well, so we have first come first, we have the priority. And for round robin, why we want to have a round robin? In fact, we have multiple queues. All right, so multiple queue, actually we have a multiple queue, Q1 and Q2 and Q3. At this moment, we still want to have a priority? No. However, we think we have 3 queues, how to have the fail treatment. So, let me mention this again, fail treatment. Because of a fairness, so we have the round robin, and also we can have waiting fail. Therefore, this one, it doesn't mean we want to have the priority. No, we want to have a fail treatment. So this one different from the priority scheduling. Well, round robin scheduling, we have queues for sure. based on the queues, we want to have the cyclically, repeatedly to scan the queues. And so that we want to maintain the fairness among queues. Fairness among queues. For example, right now we have 8 lines. Okay, allow the first student in that line 1. Okay, finish then next one, next one, next one. So this way we call it a round robin manner. Alright, so this way it's a round robin manner. As for round robin, this one, or maybe you can check the meaning in English. Well, initially, round robin, is it really fair? For example, we have the different queue size. And that one maybe not the really fair one. So we have the further enhancement, weighted fair. Weighted fair says, all right, so you should determine the different chains. If we have more packets in a queue, then we should stay there longer. All right, so stay there longer. How to state the possible duration? We can have the weight. And so that we have the generalized round robin. And therefore, we have the weight. For example, we think we have this one, it's weight 1. And weight here, do you think weight here to denote the size of a packet? It's possible to denote the size of packet. For example, for the current queue, the first queue will always have the more packets here. So we expect to be served frequently. So we can have the weight larger than the other weights in the other queues. But normally, it doesn't mean we should allow the weight to stand for the size of the queue there. No. For example, I claim my queue should have a bit higher, maybe priority. So you can include the concept of a priority by setting the weight as well. However, if you think, okay, it is not the original goal of the round robin, so we should have the fair treatment. And so that you think, okay, the weight should be some possible factor to reflect the fairness. That's fine. But I don't have the weight. Okay, for any reason, you will set the weight. Based on the weight, then you will have the weighted amount of service in each cycle. All right, okay. So based on the weight, then you can determine something like we allocate time to the queue with the corresponding weight using these. And because of this, then we think it's weighted fair. So this is the weighted fair queuing. So we have WFQ, and the weighted fair queuing, in fact, is the generalized of a round robin manner. All right. And finally, based on these, or maybe not based on these, should we have the minimum bandwidth? Maybe for the current one, you can have, okay, because of weight, so you can have the defined minimum bandwidth. And if you can define the minimum bandwidth, then you can guarantee this one. Even you want to share, so how to incorporate this further? And this is a different issue. So it doesn't mean the weighted fair queuing at this will guarantee the minimum bandwidth. No. And in fact, you can have the further principle. Should we have the guarantee or not? Well, that's scheduling, and that kind of scheduling coming from round robin, and to have a generalized version so that we have the vertical queuing. All right, and with that note, scheduling is really important, and in fact, all the scheduling design here can be refined further if we want to have the specific design. Well, and that one, it is commonly designed and discussed in the literature. So that's why we have a one page to mention. It's really important. Actually, it's really important for the issues of scheduling. Well, about scheduling, up to now, think about how many kinds of scheduling you can list. First come, first serve. Priority. Round robin. Generalized one should be vertical queuing. So if we want to treat the generalized one different from round robin, then at this moment we already have 4 types of scheduling. Actually, the general type should be first come, first serve. Second one should be priority. Third one should be round robin. And we have three main types. All right, so about scheduling, 3 main types. If you want to list the different one, actually we already have 4 types of scheduling. So this class, we start from the switching fabrics to the current discussion scheduling. And later we will continue to finish it. Before we close it, we already have the network neutrality. As for what that means, network neutrality, later we will let you know. Okay, that's it. That's take a rest. But before you take a rest, let me make sure any questions. If not, sure.